All right, so this last chapter that we're going to discuss is going to be on carbohydrates, or just sugars. And the general formula is Cn with a parentheses around water sub N. That's one way to write it down, and that actually explains why it's called carbohydrates. They are hydrates of carbon, as in if you have if you have six carbons, you will have six waters within that molecule. And you can obviously write it down as C6H12O6, which is generally what we see. But I just wanted to let you guys know that's how the carbohydrates name came along. Some common complex carbs are going to be chitin and cellulose. And obviously the like starches, amylose and amylopectin as well, but just to give you a couple examples. So the formula for the preparation of carbohydrates as well as the breakdown of carbohydrates is we need CO2 and water to form a sugar molecule as well as oxygen. So sorry I didn't balance these out, but you get the general idea. And we know that photosynthesis is the way to form sugars. And so plants, coupled with light, take CO2 and water to make the sugar and the oxygen, and then we as animals consume these sugars and metabolize them to get energy from them, and then we make CO2 and water again. So this cycle right here, though, actually the upper portion is something I wanted to mention, that there's actually an area of study where scientists are using algae and making plastics, and so they incorporate the algae into plastics to make clothing, and these clothing are now carbon negative, and so they can gather or capture CO2 from the atmosphere and in theory convert it to oxygen, right? And so that I'll send you guys a link. I thought that was really cool. Obviously it's not like the prettiest thing, but like, I don't know, who cares, right? If you're even if you have a couple of them or one of them, it's a step forward, at least in the industry, and this is the first step. So they will improve in terms of look and their ability to kind of properly function and do what we want them to do. So monosaccharides, they can range from 3 to 7 carbons, and the monosaccharides are just meaning mono. Mono means one sugar. So we can kind of define a couple things. If every sugar has a carbonyl group on it when it's in the linear form, and if the carbonyl group is on the carbon 1, it's an aldehyde, and we call that an aldose sugar, right? Or if it's at the C2, that means it's a ketone, and we call that a ketose. And we can name sugars like 3 carbon chains: triose, tetrose, pentose, hexose, so on and so forth. So let's take a look at a 3 carbon chain or a 3 carbon sugar, and we see that the formula should be C3H6O3. So there's a couple of different ways that can look. This one right here is the ketose, right? And it's called dihydroxyacetone. If you think about removing those OHs, it's just acetone, and so if you add a couple, then you got dihydroxyacetone. A little fun fact about dihydroxyacetone is it's actually in artificial sunscreens, and so it undergoes a reaction with the amino acids or the proteins in your skin. I think the dead skin, and it actually results in a browning effect. And that's what gives you that fake tan. That's why it can wash away. Hashtag fake tan, hashtag summer all year, whatever. But this is called the Mired reaction, MAILLARD reaction. And the same browning effect occurs when you cook food. So when you have that lovely browning effect on bread or your steak or whatever, that's the same thing. Sugars and proteins, or sugars and amino acids, reacting with one another. Pretty cool, right? So we're basically kind of like cooking our dead skin. Anyway, Fischer projections. We've talked about Fischer projections before, so this is going to be a review, and this whole chapter is more or less a review with a couple exceptions, and I guess those exceptions would be more so related to vocabulary. So those of you that are good with words, you're in good shape. So let's go over a couple different ways of converting structures to Fischer projections. The first way is the way your book helps you or explains it, and the second way that I want to do it is the way that I better understand it. And so at least I'm providing two different options for you. So we see the structure on the left, right? That's glyceraldehyde. If you notice, that's 1, 2, 3 carbon chain. So this is actually an isomer, a constitutional isomer of dihydroxyacetone. It's still that triose. Now, if you see the wedges and the dashes, right? Let's imagine we rotate those back. Or let's say we imagine we rotate the entire molecule back and push that aldehyde backwards, then the hydrogen and the OH are going to be sticking out at us, as shown in the next structure. They're going to be wedges sticking out at us, while the aldehyde and the CH2OH are going to be sticking backward. Now, this is by definition what a Fischer projection is, but now instead of having wedges and dashes, we actually just do straight lines. The purpose of the Fischer projection is, or the requirement of the Fischer projection is that we have all of the horizontal bonds, so like the hydrogen and the OH that are wedges currently, they need to be sticking out at us. So they have to be the wedges. And that means that all of the other bonds are going to be, the vertical bonds are going to be dashes. And this is just implied. So we need to know this as chemists when we're looking at a Fischer projection, which would be drawn on the far right in green. And so when we draw it now, all we do is just draw straight and normal bonds. And now it's assumed that those wedges and dashes are there, but we just don't explicitly draw them because it can get really complicated looking if we did have larger structures. Now, what I would like to do is show you how I would draw it a little differently. So, first of all, glyceraldehyde, the wedges and the dashes, that looks el terrible right there, because I wouldn't put the wedges and the dashes on the aldehyde and the CH2OH. I would put it on the hydrogen and the OH. That way, when you rotate it, you can draw it like this. And this looks like a normal molecule, like the normal way that we would draw it. And now, if we're looking with my beautiful little eye from the left side, we can see that the hydrogen and the OH would be sticking out or projected out towards my eyeball, right? And so, and then the aldehyde and the CH2OH would be projected away from us. Now, if you want to draw this at a little slightly more of an angle, you can see that those aldehyde and the CH2OH would be sticking out or away from us. And then it directly translates to the Fischer projection. And I just find that drawing it like a more aesthetically pleasing way on the left allows me to quickly translate this to a Fischer projection. Maybe that's just me. Do you? And as long as you get the right answer, right? Who cares? All right, stereochemistry from Fischer projections. Let's talk about this because it's not as straightforward as you would think. So let's say we've got this basic Fischer projection here. Bromine is obviously going to be 1, priority 1, and CH2OH is 2, methyl is 3, hydrogen is 4. So if we were going to go with this general rotation like we usually do, we go from 1 to 2 to 3, and that is to the right, right? So since the priority number 4 is on the vertical line, that means it's projected backwards, right? And so remember, when priority 4 was projected backwards, we could just drive the car. And if we're driving to the right, then that means we are turning clockwise or right, and that means that our configuration is R. So when priority 4 is in the vertical line, you want to stick with the rotation assignment. However, let's say we've got, remember CHO is an aldehyde. Let's say we've got priority number 4 in the horizontal plane. or dash. So our line. We've got our priorities labeled 1, 2, 3. And we go from 1 to 2. And then, sorry, it probably wasn't as clear, but what you want to do is go from 1 to 2 to 3 and then just ignore 4 the whole time. So on the above one, just make sure you're aware of that. And that also shows that we're rotating to the right, correct? But remember, the horizontal bonds are projected out at us. So remember, when priority 4 was projected out at us, if we rotated to the right, it had to be the opposite. Or we could do the thumb rule or whatever, however you got to do it. But in the case of the Fischer projection, when the horizontal bond is the lowest priority, then it has to be the opposite of the rotation assignment. So rotating to the right is not an R, it's an S configuration. Okay, so, and we're not able to just quickly, easily just shuffle things around on those Fischer projections. So it's best to just leave it the way it is, and you can't even rotate it 90 degrees because that changes the projection of those bonds. So don't mess with them like that. Just leave them the way they are, and go from 1 to 2 to 3. And if it's all right, so now what we need to do is go over an example of converting a more complicated sugar to a Fischer projection. So this guy on the left, obviously it's got 1, 2, 3, 4, 5, 6 carbons now. So it's a hexose, and it's in order to convert it, remember, to a Fischer projection, we have to make sure that all of those OHs and hydrogens that I've not drawn are projected out in one direction. So right now they're sticking up and down. But so in order to make them project in one direction, we have to convert it almost to like a ring, like I've drawn here on the right. And in doing that, we have to rotate those bonds. And that means that those OHs on the top are going to be now sticking down like the other OHs. You can see what I've done is I've kind of labeled each carbon with a red dot just to keep track of my carbons and allow me to keep track of my OHs. And so one thing to note is the OHs on the top, when you convert it to this sort of ring structure, pseudo ring structure, those are going to be the opposite sign when you convert it or when you rotate to make that ring structure, because it's basically, this is going to just take some proving to yourself and with maybe like a modeling kit or something. But when you have a OH projected up and then you rotate that bond, it's now sticking out at us, right? And so I've labeled the OH, or I'm going to label both OHs that are squared in red, and I'm going to label them in red on my new pseudo ring structure. So now you can see, starting with the OH closest to the aldehyde, it's a wedge. Now the first boxed OH is now a wedge because it's opposite of the dash. And then the next one is a dash, and then the other squared OH is a dash as well. So now all of our OHs are accounted for, and I'm looking down this, like, it looks like a little creepy crawly now, right? Where the OHs and the hydrogens are like legs. This is perfect because we want them pointing out at us. And so now what we have to do is put ourselves in that position. And so all of the wedges, when they're projected to the right like that, all of the wedges are going to be on the left. And then all of the dashes are going to be on the right in those horizontal bonds. Okay, so we start with the aldehyde on the top. The first OH is on the left. Second OH is going to be on the left. So we got left, right from top to bottom. And that's because we have a wedge, dash. Okay, and again, I've labeled the OHs that were boxed on the original molecule. I've labeled them in red again on this Fischer projection, just so we can keep track of them. Okay, so the one term, I've already given you this before, but I'll give it to you again, is the last OH on the chiral center. So this CH2OH on the bottom, that's not a chiral center, but the last OH on the chiral center in a Fischer projection If it's on the right, then that means it's a D sugar. So dexter for D, it means right. And if it's on the left, then that means it is an L sugar. And that's how we kind of classify our sugars, just looking at where the OH is in the end. Very straightforward. Let's cruise through this one. We're going to go move pretty quickly. This sugar right here looks very similar. However, the wedges and the dashes are going to be different. Don't look at the previous one. That way you can just try. Even if you did the same problem again, it's still good practice, because this is the part where drawing the ring is a little bit tricky maybe. So again, label those out, count the number of carbons and make sure that you're good. Box those hydrogens and make sure that they're opposite of like wedges and dashes from what you start with. So now the dash wedge goes to a wedge dash. And now we just have to convert it to a Fischer projection. So remember, we're looking from the right side in to the left. So and that means that all of those wedges are going to be on the left, and then any dashes are going to be on the right. So you should be able to fairly quickly draw left, 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 right for all of the OHs. Now, sometimes I like to omit those hydrogens, but I'll just draw them in for you, so just for clarity for now. But if you ever see me draw just the OHs, that's because the hydrogen is just implied. Okay. All right. So that is basically how you convert regular linear chain sugars to Fischer projections. Now we want to go over kind of a couple terms or it's a little vocabulary, right? So we're going to compare D versus L versus just completely different sugars altogether. So let's say we've got this sugar here. The hydroxyl groups go right, left, right, right. So remember, those are all chiral centers, okay? Now let's say we had another sugar where they went, instead of right, left, right, right, they go left, right, left, left. Now this is a mirror image, right? If those are all the same, if those are all chiral centers and they're all opposite, this is just an enantiomer. Now, sugars that are enantiomers of one another are just D sugars and L sugars. So like D glucose versus L glucose. And this is because every stereocenter is opposite, okay? Now, let's see a sugar. I'll draw glucose again. So we got right, left, right, right. That's how I remember glucose. Let's draw another sugar where we have left, left, right, right. Okay, so notice that not all of the OHs are opposite, right? So these two right here are where the difference is, and these other ones are where they are the same, okay? And now since we've got just a difference in one chiral center, this is pretty much just a diastereomer, right? But when it comes to the sugars, and just in general, it's an epimer, okay? So there's diastereomers that differ at only one chiral center, okay? Another thing, while we're on the topic of chiral centers or stereogenic centers, remember that when we have a certain number, or like let's say we have n number of stereogenic centers, that means we can have 2 to the n isomers that are possible. Okay, so in this case, we have, in this sugar glucose, we have 4 stereogenic centers. That means 2 to the 4th is equal to 16 possible isomers. And this doesn't have to be the case because we could potentially get symmetry or whatever, but in the case of glucose, we actually do have 16 isomers, and where 8 of them are D sugars and 8 of them are L sugars. So it's important to note that we only care about 8 of them because our bodies can only process D sugars, and those are the naturally occurring sugars. Just like amino acids, there's a naturally occurring L sugars or L amino acids. So for physical properties, I feel like these are going to be pretty obvious. They're going to have high melting points and they're going to be super soluble in water, right? That's all I'll pretty much mention about physical properties, but of course I usually have you guys take a look at that on your own. So do that. The next topic that I wanted to discuss in detail is Haworth projections. So remember, we did this already when we were talking about acetals and hemiacetals. We did this already. So this is going to be, again, a good review for you. But there are going to be some terms in there that we need to know as well, and I think you'll find them useful. So a 6-membered ring would be a pyranose, and a 5-membered ring, sugar, that is, it would be a furanose. And so these, as they are hemiacetals, right? And so remember, hemiacetals are pretty reactive, and so this is important in terms of reactivity of sugars. So let's say that we actually drew the stereochemistry in for these sugars. Now, the OH can be projected out at us or away from us, and these two things are called anomers. Okay. Now, these anomers are pretty much, I've starred the anomeric carbon by definition, and the anomeric carbon is where the carbonyl group used to be before the alcohol attacked it and made a hemiacetal. So anomers are differing positions at the anomeric carbon. So if it's a wedge or a dash, right? And so this will be more clear when we actually draw the linear sugar and convert it to the Haworth projection, okay? Which again, we've already done. So I hope you understand what I mean when I say carbonyl group that is attacked by a hydroxyl group. So first we have a Fischer projection, and then we rotate it 90 degrees. Now we just draw those right, left, right, right are now down, up, down, down for the hydroxyl groups, okay? Now we also want to rotate the rest of this sugar chain around in a suggestive manner that kind of indicates that we're going to form a 6-membered ring. And so when we do that, we still want to put our OHs down, up, down, down. So here we go. If you need to keep track of them, you can label all your carbons with red dots. And but we can see that our hydroxyl groups are down, up, down, down now. And so if you remember from our previous discussion, you know that the OH group on the 5th carbon is what attacks the carbonyl carbon to form the new hemiacetal, right? So we need to rotate that bond over there to put it in a position where it actually makes sense to attack. And so that's what we've done for this new structure. Now, this oxygen is put in place perfectly to do the attacking of the carbonyl group and form that hemiacetal, as well as the 6-membered ring sugar, the pyranose. So, let's redraw that. And when we do this, it's important for us to note that the CO bond, or the CO from the aldehyde, is actually an OH now. So we've created a new stereogenic center, and that by definition is the anomeric carbon. For D sugars, the C2OH is always going to be up, and this is just due to the way we form that cyclic sugar. And the alpha anomer is going to be opposite. Okay, and that means that the beta anomer is going to be on the same side. So another way we can state that is the alpha anomer is going to be trans, and the beta anomer is cis. Okay. And this is because, as I just showed in the mechanism, at some point we have a carbon-oxygen double bond that's resonance stabilized with a positive charge on that oxygen, and that means that it's planar, and we can have the nucleophile attack from the top or the bottom. So this red oxygen can attack from the top or the bottom, and that gives you your two different anomers, alpha and beta. Now, the Haworth projection can be converted to a sugar with wedges and dashes, and this is going to be fairly straightforward. So any sugar or any OH that goes up in the Haworth projection is going to be a wedge because it's coming out at us, and any OH going down is going to be a dash because it's pointing away from us. And so we have this. So it's all. The next portion of this discussion is going to be an equilibrium discussion. So we have alpha and beta anomers, but we'll come to find that one of them is more stable and one of them therefore is more preferred. And so how do they go back and forth from beta to alpha and alpha to beta? Well, this is a hemiacetal, remember, and the hemiacetals can be converted to their original carbonyl compounds. And so that's exactly what happens. We open up that cyclic sugar, and that gives us the linear sugar via a hydrolysis reaction. And then that linear sugar can then undergo an intramolecular hemiacetal formation again. But again, one of the intermediate steps has a planar sp2 hybridized carbon, and therefore the red oxygen can attack from the top or the bottom. If it attacks from the top, then we will get the OH projected down, and that would give us the alpha anomer circled on the right. And if it attacks from the bottom, then the OH would be projected up, and that gives us the beta anomers, 63% on the left, circled on the left. Now, this process of opening and closing of the sugars is called mutarotation, and it only occurs because we have hemiacetals in these sugars. We'll come to find later that those that don't have hemiacetals will not open and close like this. So why is the beta anomer favored? Well, what we want to do is draw this in the boat formation, or chair formation. And we'll look at the OHs and see where they are. So this is going to require us to remember our up C's, down C's, and also our up substituents and down substituents. So the ones I highlighted in blue are circled in blue on the beta anomer above, and the ones highlighted in red are circled in red on the above sugar as well. And you can see that all of the blue are up, including the OH at the anomeric carbon. So since that OH group is up, then that means it's a beta anomer. And also, I indicated in the past discussion that beta anomers also have that OH group in the equatorial position. And then therefore the alpha anomer would be in the axial position, alpha axial, and it's axial down, and so it all kind of comes together. Just now we're adding a couple of different words like anomeric carbon and anomer. So that's why the beta anomer is more stable, because the OH group is in the equatorial position. Now what I want you to do is draw an acyclic hydroxyaldehyde and also a six-membered ring with the wedges and dashes. I would just do the six-membered ring with wedges and dashes first because that seems to be the easiest. So just draw out the six-membered ring again, and then we have our OHs that are pointed down in the Haworth projection. Those are going to be dashes, and then those OHs that are up are going to be the wedges. So I've highlighted the anomeric carbon in blue and the nucleophilic oxygen in red. The bond in between those two is the new bond that's created, and if we move our way back, retrosynthetic analysis, we can draw our ring like this with that bond cleaved, and we know that the red oxygen was a hydroxyl group, and we know that the anomeric carbon that's blue was an aldehyde. And now from there we can just fill in the OHs accordingly, knowing that the red oxygen, since it's a D sugar, was pointed down. Now that we've done that, we can convert to a Fischer projection by imagining rotating this aldehyde to 90 degrees to the left, and then all of the up OHs are left and the down OHs are to the right. And there you have it. It is also important to note that this is a way to prove to ourselves that when the CH2OH is up, that's a D sugar. And so because we just went from an up CH2OH and then worked our way to the Fischer projection, and we got a D sugar. Let's try another one. The sugar drawn on the left is a Fischer projection. Draw the alpha anomer. Okay, so when we have an alpha anomer, remember that is either an axial down OH or it is trans to the CH2OH. If it's a D sugar, so we have a D sugar, and that means that its CH2OH is up. So the alpha means that it is trans and it's also axial down. So let's draw our six-membered ring with the anomeric carbon highlighted in blue and the OH hydroxyl group highlighted in red. The reason why we did a six-membered ring is because this particular aldehyde, if you can form a six-membered ring, you will form a six-membered ring, and that's because, remember, six-membered rings are more stable. And so the pyranose is what's going to occur in this case. And we can work our way through as usual. All of the hydroxyls are to the right, but if we tilt that 90 degrees to the right, we see they're all down, and so we draw a Haworth projection with all of our OHs down. And in addition to that, we also have an alpha anomer, so that's why the anomeric OH is down as well. Okay. You can work through those slowly on your own. But again, we've done this before, so we're moving fairly quickly. So let's try and convert another Haworth projection to a Fischer projection. Okay, so highlight the nucleophilic oxygen and the anomeric carbon. The CH2OH is up, so that means it's a D sugar. And the OH is down on the anomeric carbon, which is important for us to know that it's alpha, but it's not important to indicate, or it's not actually useful information to help us get to the final Fischer projection because it doesn't matter. But I just want to remind you guys of what is what. We do know also that the anomeric carbon came from an aldehyde. So let's cleave that anomeric carbon oxygen bond and draw our sugar, with the anomeric carbon now being an aldehyde and the red oxygen being an OH group. So we have a down, up, up hydroxyl, and working our way backwards, we will be able to rotate that aldehyde, draw the Fischer projection, and boom, there you go. Since my OHs are down, up, down, in my open sugar, we will have the hydroxyls on the Fischer projection as right, left, right, and then the red oxygen is always down in this case for the D sugars, and so it's to the right as well. So let's move on to furanose. Furanose, remember, is that five-membered ring for the sugar. Okay. So furanose is usually going to be created from aldopentoses, which means that you'll have a 5-carbon chain for your sugars, and an aldehyde in the terminal position. Or it could be from a keto hexose. Now, what does a keto hexose look like? Remember, in the beginning, if the carbonyl group was at the 2 position, then it had to be a ketone, and so we will have a 6-carbon chain with the ketone at the 2nd carbon. The reason why this forms 5-membered rings is because that hydroxyl group at the last one on the right is what does the attacking, and that is attacking the carbonyl group, and so those are only going to be 5 members within that ring. Okay, so the structure on the right is fructose. The one on the left is D-ribose. Okay. Now, if we should be able to pretty much jump straight to the Haworth projection if we understand, if we kind of number all of our substituents. So the carbonyl group being 1, work your way down until you reach that last stereogenic carbon with the OH, and that OH on there is going to be the nucleophile attacking to form that hemiacetal. So in this case, D-ribose forms the structure on the bottom. And I've labeled them the anomeric carbon, the red OH, and also numbered the carbons for you just for clarity. And for fructose, it's the same thing, except now, since we have on that anomeric carbon, the carbonyl group, we had a CH2OH substituent on there, so we'll have that in the final product as well. And this would be beta D fructose. And the one on the left for ribose would be the alpha D ribose. All right, so the next topic that we want to go over is glycosides. Glycosides, we've already actually seen them, we've created them, and they're pretty much just acetals. Okay, so they're just called glycosides because they are done with sugars. So if we have a sugar drawn here, HCl and an alcohol, remember we need an acid and an alcohol, that's going to form a glycoside or an acetal. As long as we got that hemiacetal on the left, that's the only thing that's going to react. Remember, because it's not a normal OH group, it's part of a hemiacetal that can get protonated and leave as water, and that carbocation that forms can be stabilized by the adjacent oxygen. Whereas the oxygen on the upper left of that sugar, just as an example, would not be able to be stabilized by resonance, and so they don't react the same. So after we do have water leave and stabilize that resonance, that oxonium can be neutralized with the attack of an alcohol. After the loss of that proton, we get to the final acetal product, or the final glycoside. Again, we've done this before, and this is just a review. So something we didn't go over explicitly before is a couple other reactions, but we do know the general mechanism for this reaction because we have gone over those. So AC2O is an acetic anhydride. ACCl is acetyl chloride, and then silver oxide and methyl iodide. We've seen those before, and we know that silver oxide is a base. And I'm just going to draw that structure for you. The AC is the acyl or acetyl, and it's just a carbonyl group with the methyl on there. We know that OHs or oxygens are nucleophiles, and they can attack very electrophilic and reactive species such as acetic anhydride and acyl chloride, and you can actually substitute that hydrogen for an acyl group or acetyl group, and then you can also do the same thing with silver oxide and methyl iodide via an SN2 reaction. Just deprotonation, removal of that hydrogen, and then attack of the methyl iodide gives you the methylated product. So glycosides do not undergo mutarotation, and that's because we can't form a carbonyl group with the R group on there, because that's not going to be as easy to remove, whereas the oxonium that forms in the intermediate for the formation of an aldehyde it's got a proton on it, and you can just deprotonate that. Review the mechanism for that if you don't quite understand, but otherwise just know that glycosides do not undergo mutarotation, and so when you can isolate an alpha or beta anomer, they won't switch back and forth, whereas with the hemiacetal, if you isolate a beta anomer and you put it in solution, you'll end up getting that like 67 or 63-37% mixture like I mentioned before. That's just as an example, those percentages. Other ones might vary. Okay. So the reduction of carbonyl groups. Again, we know how to do that, right? So let's just look at an aldehyde. We've got sodium borohydride and an alcohol solvent. That's what does sodium borohydride do to carbonyl groups? It converts them to alcohols, and that's exactly what happens in sugars as well. These are called reducing sugars because you can reduce them. So also this final product is an alditol. That's just a generic name for the product of an aldehyde and a sugar being reduced. Now what we can do is discuss oxidation of carbonyl groups in sugars as well. So again, we know how to oxidize aldehydes, right? Or ketones for that matter. So the Tollens reaction or Tollens reagent that use silver oxide and ammonium hydroxide. We know that this converts aldehydes to carboxylic acids, and there are a couple other ways that are known to be used for oxidation of sugars, and that is some source of copper 2 plus or bromine and water if you want a higher yield. That way you can move forward with the reaction to carry this oxidized material to do more. So those three are going to convert your aldehyde to a carboxylic acid, whereas if you wanted to oxidize the terminal CH2OH, you can use nitric acid and water, and that converts both sides to a carboxylic acid, giving you something called an alderic acid. Whereas if you only converted the aldehyde to a carboxylic acid, that would be called an aldonic acid. And now remember, since these reactions occur only on the linear sugar, because we have that carbonyl group, that means that you can't reduce or oxidize glycosides because there's no population of that linear sugar present. Non-reducing sugars as well, that would classify them as non-reducing sugars. And then another thing to note about these particular reactions is that specifically for alderic acids, some of the sugars that are the alderic acids that you form after the oxidation may be achiral due to symmetry. So we know that sugars are helichiral. They got a lot of stereogenic centers in them, and so by definition they are going to be chiral without that symmetry element. However, this example right here, if we were going to convert this sugar to an alderic acid, we have those three hydroxyl groups on the right, and we form two carboxylic acids on either end, and therefore we have a high symmetry element here. So therefore this would be an achiral alderic acid product. Okay, so again, it's important to note that this reaction won't occur for glycosides, and that's by definition calling them non-reducing sugars because they aren't reactive. So the next portion of this discussion is going to be on disaccharides, which means two sugars. And so we've seen these also before. I showed you lactose and mannose and maybe a couple other ones, but we're going to show you again just as a refresher, and because this portion is actually really fun. I enjoy I enjoy sugars in general, but the polymeric aspects of them and what they can actually do, how they differ in structure is really cool. So this structure here, we have note in a hemiacetal on the terminal end on the right, circled in blue. That means this portion can actually open and close. It can undergo mutarotation, whereas there is an acetal in the middle of these two, and that's not going to break open as easily. So this is maltose, and they are two glucose molecules connected to one another via something called a 1,4 alpha glycosidic bond. And it's called 1,4 because the one position of the above sugar is bound to the fourth carbon on the lower sugar, and it's a glycosidic bond because it forms a glycoside that's basically an OR group sticking off of it in the form where R is the sugar. And remember, we can hydrolyze these bonds with strong acid, and that will give us two glucose molecules here. So lactose has a slightly different structure, and that's where we have our sugar point projected downward, because now it's not an alpha bond, right? Remember, when the CO bond is equatorial, that is a beta bond, right? It's the beta anomer. So this is a galactose sugar and a glucose sugar connected via a 1,4 beta glycosidic bond. And this is, again, because that CO is in the equatorial position. Also, the reason why we know that it's a galactose sugar is because it's got the same position for all the OHs except for that one highlighted in red. That basically we'll come to find, we'll learn that those are the differences in the sugars are really easy to identify. One thing about lactose that we all know is that some people are lactose intolerant, and we can't really break down those beta glycosidic bonds, and the acid hydrolysis doesn't work well in that case, and so lactase is the enzyme that breaks it down for us. And if people lack that enzyme, then they end up they're lactose intolerant, and so they have all the negative symptoms associated with that. All right, now the next dimer or disaccharide that I want to go over is obviously super common, and that's sucrose. That's just your table sugar, and that consists of a fructose molecule as well as a glucose molecule. Now remember fructose is a furanose, which is a 5-membered ring, and so this is my sad attempt at drawing that, and I've labeled the glucose and the fructose for you just so you know, but that's all there is to it, right? I just want to kind of show you what that looks like, and kind of point out that that is the table sugar that we work or eat every day. So, or maybe not every day. I don't know if you're good, but I do. All right, so there's also fake sugars as well, and the fake sugars, some of them have what looks like a sugar molecule in it, but some of them don't, which is kind of interesting. And you might wonder, well, how did they end up finding out that it was useful for fake sugar? And that's because they were all prepared by terrible scientists who actually tasted their chemistry, and so inadvertently or on purpose. So remember, always wash your hands after cooking, after doing chemistry, whatever. Wash your hands, and but if you don't, maybe you'll discover something new, like saccharin, aspartame, or sucralose, all of which are fake sugars. Something interesting about aspartame is that it's made from phenylalanine, or it can be broken down into phenylalanine, and so those who have a sensitivity to phenylalanine and can't process it are not actually allowed to have aspartame. Mother Nature does it best anyway. All of those are synthetically made, so we don't want those. I don't. So, polysaccharides. Those are basically poly, meaning many, sugars. And so there's a few different forms, and one of them that we are very familiar with is cellulose. The other two are amylose and amylopectin. Those are starches. Cellulose is a linear chain, and that's because it's connected via a 1,4 beta glycosidic linkage, whereas the amylose and amylopectin are connected via a 1,4 alpha glycosidic bond, and amylopectin is highly branched and is also connected via a 1,6 alpha glycosidic bond. Our body stores sugars or glucose in the form of glycogen, and in our body it stores it in our liver as well as our muscles. And glycogen has a similar structure to amylopectin, but it's actually more branched. So just to give you an idea, cellulose, the reason why our body can't process it is because of that 1,4 beta glycosidic bond, and cows can process that and because they have the proper enzyme, and as well as other grazing animals. So another important aspect of cellulose is that it's not soluble in water. But how is that possible when it's consisting of sugar monomers that are super soluble in water? We've got a ton of OH groups. Well, that linear aspect of cellulose, because the 1,4 beta glycosidic bond, allows the linear chain to stack on top of itself to form a large network of polymers that stick together via hydrogen bonding, and since it's almost like it creates a super molecule that won't dissolve in water. Super cool stuff. What I find even more cool is human milk oligosaccharides. So oligosaccharides is like just a few saccharides. Together, we've got this bad boy here with some acetal bonds as well as some hemiacetals. Remember, these acetals in the central portion of this HMO is not going to be broken down in our gut with even the acids in our gut. So it actually promotes the formation of good bacteria in babies, as this human milk comes from the mother, obviously. And it also promotes the excretion of pathogens in the poop, because this HMO is not digested by us, but pathogens actually link to them. And so any harmful things in the body are kind of excreted out in the poop attached to this HMO. So this is one of the reasons why mother's milk is badass, because it just provides so many benefits to the child, and there's still a lot more that we don't understand about mother's milk, so still being studied. Another sugar derivative which is super cool is glucosamine, which is pretty much a glucose molecule with one of the OHs replaced with an NH2. Now this NH2 is nucleophilic and can undergo a chemical reaction with acetyl-CoA drawn over the reaction arrow, and that gives you this new amide sugar. Okay, and this amide is called N-acetyl D-glucosamine, also known as NAG, N-A-G, and NAG or NAG is the monomer for chitin. Now, as you know, chitin makes up the exoskeleton of shellfish, right? So like crabs and stuff. So how is this super polar monomer not just dissolved? Like, how does it make up their exoskeleton of marine animals? They're all up in the water. Why aren't they just dissolving away? Well, that's because they got stacks on stacks on stacks of this monomer, similar to cellulose. They form a large network of hydrogen bonding polymers, and therefore only the surface is exposed to the water, and that's not enough to actually dissolve the molecule or dissolve their exoskeleton. So that is super cool. It just goes to show you again how strong hydrogen bonds are, right? Stacks on stacks on stacks. I'm gonna go ahead and leave that guy there for you, just cause, why not? The next portion of the discussion is N-glycosides. And so let's say we have this sugar molecule here, and in the presence of mild acid, we form this oxonium intermediate. Remember, this can be attacked by a nucleophile. Usually we've seen it as being attacked by water or an alcohol, but why not an amine? So if we threw an amine in there, we could form something called an N-glycoside. All right, well, cool story, bro. Why do we care? Well, because it works the same for furanose. Again, why do we care, right? Well, because it's essential to life. So let's say we have this guy here, D-ribose, as well as the structure on the right, where we actually, that's not an accident, I'm missing an OH. That's because this is called 2-deoxy-D-ribose. Now it might be starting to click why this is important, right? N-glycosides can actually be formed with these two sugars and form ribonucleosides with the ribose on the left, or deoxyribonucleosides with the structure on the right. Okay, and it's done in the same manner, where that nitrogen is going to come in and attack an oxonium intermediate. But now our nitrogen nucleophile is very specific, a very specific base, right? And they're all going to be very, very similar structures to one another. And so that makes it easy for us to remember them. So we've got these guys here, and with a 6-membered ring, we have cytosine on the left, uracil in the middle, and thymine on the right. Note, they're very similar structures, right? We also have a couple others that are going to be made with 2 fused rings together. So These are going to be your adenine and your guanine. And again, made from two very similar structures, with the two heterocycles fused together. Remember, a heterocycle is a ring containing heteroatoms, meaning not carbon. So our adenine and guanine, all of these are going to have the nitrogen that I'm circling in red act as that nucleophilic nitrogen to form the N-glycosides, or the ribonucleosides and deoxyribonucleosides. It's always going to be those nitrogens whenever you're using those bases. But wait, hold up, wait a minute, don't go there because I ain't with it. I thought it was called a ribonucleotide. Well, we're not there yet. So when you react, let's say, cytosine with ribose, you get a ribonucleoside. It doesn't become a ribonucleotide until you react that CH2OH group with a phosphate. So that OH is replaced with an OP bond, and only then do you get a ribonucleotide. Now I'm just going to go ahead and leave that there for you, because we're done with science for the day.